consider the nature of what I call blackbody radiation. The most common example of blackbody radiation is the light that we get from the sun. It was shown by Isaac Newton that if you get incident white light, incident sunlight on a prism, it would decompose this into its composing wavelengths. The longest wavelength in the visible part of the spectrum is red, and the shortest wavelength is violet. But in astronomy, we usually use blue. You're going to see many times in astronomical texts saying that the spectrum goes from red to blue. It's not that we are ignoring violet, it is just astronomical parlance. So this is what I call one of the first laws of spectroscopy. Spectroscopy is the study of the interaction between matter and radiation as a function of the wavelength or frequency of that radiation. So this law states that a hot solid or a hot dense gas produces a continuum spectrum. You have here, in this case, a lamp, so either a hot solid or a hot dense gas. You pass the light through a prism that is decomposing it into its wavelengths, and what you see is a continuum spectrum. You see all of the colors from red to blue. And the name blackbody comes from the definition of these bodies. We call a blackbody a body that is a perfect absorber. It's a body that absorbs all of the radiation that is incident at it. Now, if the body is in thermal equilibrium, if it is absorbing all of the energy that is directed at it, to maintain the same temperature, to maintain thermal equilibrium, it has to re-emit the same amount of energy. So a perfect absorber is also a perfect emitter. Now, this is only showing what colors are present. Another thing that we can do is measure how much light in which wavelength, how much energy, what is the intensity, what is the brightness of the light as a function of the frequency or as a function of the wavelength. When you do this analysis, this is the curve that you get. So plot here in the horizontal axis is the wavelength, and in the vertical axis is the intensity of light broken down in its constituent wavelengths. So here have the shortest wavelength blue, and then green and yellow, orange, and then the longest wavelength red. Now, there are other wavelengths. There are wavelengths that are shorter than violet, that our eye cannot see. We call this ultraviolet. And there are wavelengths that are longer than red, that we cannot see either. These are called infrared. What is shown here is this rise in the ultraviolet part of the spectrum, a peak here in the visible. This is the shape of what I call the blackbody radiation curve, which was first explained in its modern form by Max Planck. So this curve here, the shape of this curve, we also call the plunk curve or Planckian. These are also terms that you're going to see in astronomical texts. It is apparent that this shape is only a function of the temperature. So different black bodies of different materials, if they are at the same temperature, they are going to give you the same curve. The intensity as a function of frequency is going to be the same. It doesn't matter if the body is composed of iron, or steel, or ceramic, or just dense bulk gas. If they are radiating as a black body, they are going to have the same curve if they are at the same temperature. What you're seeing here then is a blackbody curve of 6,000 Kelvin, which is roughly the temperature of the sun. As you see, it peaks on the visible part of the spectrum. So it is not a coincidence that our eyes are sensitive to light in this peak. That's where the most abundant offer of radiation happens to be. If we had eyes that saw in, say, gamma rays or X-rays, or eyes that saw in microwave or radio, they would be less efficient. They would be less useful than the eyes that we have that see in what I call the visible part of the spectrum, which is where the sun peaks. Stars usually have temperature around this range from 3,000, that's the temperature of the coldest stars, to 10,000, 20,000 Kelvin, which is the temperature of the hottest stars. The hotter stars will peak in ultraviolet, and as you go down in temperature, as you lower the temperature, this is the black body of a star whose temperature is at 5,000 Kelvin, they would peak in red. Stars cooler than that peak in infrared, and we see part of their emission in visible wavelengths. As you go to a star that is at 3,000 Kelvin, the peak of the emission is far in the infrared, and only part of their radiation is emitted in visible wavelengths, mostly in red that we see. That's why cold stars look red to us, and hot stars look bluer to us. The human body peaks at 300 Kelvin, So its peak is at 10 micron. It's far to the right of this picture. We're not seeing here in this scale. All right, so how is blackbody radiation emitted? What is it that we mean by blackbody radiation? Well, blackbody radiation starts with the emission of a single photon when you have an electron in the electric field of a proton. Inside of the atom, the electron is bounded to the proton and cannot radiate. But if the electron is free, this electron is going to radiate a photon. And if you had many, many electrons, then you're going to have photons of all wavelengths being radiated. Now, to understand how we pass from a situation like this, where you would radiate photons of any wavelengths, into a shape like this of the Blackbody curve, we need to invoke the principle that Planck used to describe this curve, which was to assume that the energy of the photon is proportional to the frequency. To understand how we get to the blackbody shape of the curve, to the Planckian curve, we needed to consider the assumption that Planck used to describe this radiation, which was later shown to be correct. He made the assumption that the energy, E, is proportional to the frequency, nu. The proportionality is H, which is called Planck constant. The energy being proportional to the frequency means that photons of very low frequency, that means photons of long wavelength, have lower energy than photons of higher frequency, shorter wavelength. So a blue photon, blue, low wavelength, high frequency, is more energetic than a red photon. Red photon, longer wavelength, lower frequency. So if you have a huge collection of electrons that are emitting and absorbing photons, these electrons, they are going to both emit and absorb the long wavelength, the low energy photons. So that explains why you have this long tail of the Planckian distribution. The low energy photons are easily absorbed. Whereas for the high frequency, the ultraviolet part of the spectrum, what is going on is that the electron cannot emit a photon of more energy than its kinetic energy. The electron is going on the electric field of the proton and is emitting a photon. The energy of this photon comes from the kinetic energy of the electron. So the electron cannot emit a photon of higher energy than its kinetic energy. And the kinetic energy of the electrons is given by the temperature. You have that this tail here comes from this fact that the electron cannot emit a photon of higher energy, that means of higher frequency, than the energy equivalent to its kinetic energy. And then you see that at a higher temperature, you have more photons because the electrons are more energetic. You have higher energy photons going into the ultraviolet than you have at lower temperatures. At lower temperature, the electrons are going at lower speeds. So there are not that many electrons that can emit a very energetic ultraviolet photon. So that leads then to this correlation between the temperature and the Planckian curve. And as you see, the maximum wavelength, the peak of this Planckian curve, is a distinct function of the temperature. Here you have the peak wavelength of 6,000 Kelvin, the peak wavelength of 5,000 Kelvin, peak wavelength of 4, peak wavelength of 3. They follow this very clear line. This is called Wien's displacement law. Wien's displacement law states that the peak of the blackbody distribution times the temperature is constant. That means if the temperature goes up, the peak is going to be displaced to shorter wavelengths. And if you go down in temperature, the peak is going to be displaced towards longer wavelengths, lower energies. So that the peak wavelength times the temperature is a constant, and this constant is given by this number. Here, mk, m is meter, and k is Kelvin. So you see, you put here a peak wavelength of 6,000 angstrom. That will correspond to a temperature of about 6,000 Kelvin. If you put a temperature, say the temperature of the human body, 300 Kelvin, it's going to give you a peak wavelength of 10 microns. And this is what you expect of stars. If you use Wien's displacement law for stellar temperatures, there you have here a temperature of 3,000 Kelvin. You put on Wien's displacement law, the peak wavelength set at 10,000 angstrom, which is 1 micron. Put the energy of, if you put the temperature of the sun, 6,000 Kelvin, the peak wavelength is 5,000 angstroms. That peaks around here in the center of the visible spectrum. If you go to a much hotter star, 12,000 Kelvin, the peak is going to be displaced to 2,500 angstrom. That's far in the ultraviolet. And this is the curve that traces the peak. The peak indeed falls with 1 over the temperature. This explains why cold stars are red and hot stars are blue. When you look at the night sky and you see a red star, it is a cold star. The temperature is about 3000 Kelvin or lower. Stars like the sun, yellow, are kind of rare. You don't see them many in the night sky, but there are a few of them. They are of temperature about 6000 Kelvin.